altitude of 700 to 900 kilometers, going around the Earth every 90 to 100 minutes, so it's 14 to 16 orbits a day. It means the satellites are moving 7 kilometers a second. It gives us, to a good approximation, equivalent quality data anywhere in the world. So when you think about the places in the Earth that are hard to observe, ice sheets, polar oceans with sea ice, mountain glaciers, open ocean, tropical forests, boreal forests, and just in general undeveloped areas where you don't have the research infrastructure. The satellites really let us see all of them, more or less with the same degree of quality. And this is the first time in human history, really, that we've had that we're not restricted to knowing about where we are. And we get the information, we distribute it, we share it, so that it benefits everyone. The satellite orbits may look like they're sort of random. They're not. Most are in polar sun-synchronous orbits, so they're over each pole at 14 to 16 times a day, so it gives us very good coverage. Some of them are set up to go together. That's what we call our A-train constellation. It includes the Aqua, Aura, CloudSat, Calypso, OCO2 satellites. It gives us the benefits of near simultaneity, but without having all those instruments on a single platform, which we really could never do. We built the constellation up over a period of years. It includes the Japanese satellite in the constellation, and there was a French satellite in the constellation, but at its age that came out, so it sort of flies close to it. So for some things, especially for atmospheric observations, being able to look at the same region of the atmosphere with a diversity of techniques at about the same time is really important. One pair of satellites you'll see, Grace 1 and Grace 2, those are very close together. That's from a cooperation between the US and Germany. There, the two satellites, the distance between them varies depending on the gravity of the part of the Earth that they're flying over. And you can sort of invert that variation in gravity to get information about the mass of the Earth below, which in many cases relates to how much water there is, whether it's liquid water stored in the ground or ice at the surface. So it's a variety of different things. ISS is the International Space Station. That's a platform that's got astronauts living on it all the time, but it's becoming a platform for Earth viewing. That's in a mid-inclination orbit that only goes up to 51 degrees north and south to 51 degrees south. So you get a little bit of a different view of the Earth that way that can complement some of what we're doing. So next, what I'll do is give you one of these sort of great views of the Earth. This is night lights from an instrument called VIRS on the Suomi National Polar Orbiting Partnership satellite. It's a partnership of NASA and NOAA, U.S. Department of Defense. It was launched in 2011, and it's got a special band that we call it a day-night band. What this does is this shows us where we are, and not just where we are, but especially those of us who are fortunate enough to be able to have the lights on at night, because there's parts of the where you don't see them. That means there's either no people or there's people who don't have night lights. But when you think about the stress that we may put on the Earth, the stress tends to come from large numbers of people and large amounts of industrial development, and that will tend to be reflected in night lights. So mostly what you see are the big cities and the corridors between them. There may be a few things where you'll see places that may not have a lot of people, but may have a lot of industrial activity, some oil work in Canada. You might be able to see some areas with fishing boats. And it's a great insight into human geography. You can even see borders, essentially, in some cases, like South Korea, North Korea, because there's differences in what's going on in those countries. So it's a great way to look at us. As I said, something there may be fires like you'll see, but in general, it's people and night lights. So next shows something else that's really a driver for the Earth, and that's the biosphere. This shows the terrestrial biosphere as well as the biosphere in the ocean. It'll go over the sort of a seasonal cycle that you can sort of see it run through there. The land vegetation, green is when things are growing, and brown is when they're not. And for ocean chlorophyll, blue is where there's not much, and then sort of pink is where it is. But You can certainly see the effects of the seasons and see in the tropics there's less of a seasonal variation. But this is sort of like, you can almost think of the Earth as a living, breathing creature in some sense. And this is planetary scale metabolism. And especially when you're thinking about carbon dioxide, this is the biosphere. That's what can take up carbon dioxide, but it can also put it back into the atmosphere. So when you then combine this with the natural biosphere, and then with what humans are doing, that gives you both a lot of the forcing that takes place on the surface to the Earth, what we're doing, but what the Earth does as well. You need to understand both if we're really going to understand the Earth. So next, let's see, next shows another example. This is the Las Vegas, Nevada area from 40 years of Landsat data. So it goes pretty quickly, but you can see how much development there is in Las Vegas. The reds represent areas that have some water in the soil, and the grays tend to represent areas that have been paved over. But what you can see now, it's going to slide back and very quickly take you back from 2014 to 1972. So this is one of the most rapidly growing areas of the U.S. And you can see we've literally changed the face of the Earth in a very significant way, in a way that's completely visible from the altitude of space. So it's happening, we know it's happening, we can see it. But information like this isn't just so we can sort of gawk at it and say, wow, that's a big change. This becomes the raw input for scientific study, because we can begin to look at, what does that mean for the way solar radiation interacts with the surface? What does it mean for an urban heat island that we might get? What does it mean, if and when they get precipitation? How is it going to vary between runoff and infiltration? By having the quantitative data about the Earth system and how that's changing it, that's the raw material that we use for scientific study in the field we like to call Earth system science, where we're really looking at putting all the pieces of the Earth together. And I showed this for Las Vegas, but again, you can do this for other parts of the world. Come back next week to one of the hyperwall narrations, you might see us do the same thing for Dubai, over a series of images. Different part of the world, but we can provide the same kind of information. Next shows something else that's important to the Earth. This is the vegetation is there as well, but now you can see fires. The red dots represent fires. It comes from the MODIS instruments. It's fly aboard the Terra and Aqua satellites. We launched them on the Terra in 1999, so it's a 16-year satellite. But you can see the seasonal march of fires, where different parts of Africa, you see them in different parts of the year. In some of the higher latitudes, you'll tend to see them from lightning strikes. And in some areas, it's for agricultural land clearing that people use, whether it's deforestation or it's just stuff the way that people clean off the land. But you can really get a sense of where the fires are. And again, from the point of view of having environmental information, I think that the satellites are wonderful for this, because if you're talking about being able to see so many fires all around the world every day, in very, some cases unpopulated areas, or in other cases areas that are populated but undeveloped, that really don't have the kind of instrumentation that you would need, let alone the data distribution mechanisms, but the satellites are getting it. But again, it's not just the fires themselves, because what that does is that becomes input that you can use into studies about, what happens to the land that's burned. You can match it up with land cover data and look at that and look at it recover. You can think about, what do all those fires mean for air pollution? What does it mean about CO2 and carbon monoxide in the atmosphere? What does it mean for particulates, and then what happens to those particulates? So you get this data and you start putting it together with other data, and that's where you really can sort of see it through from the forcing to the impact. And again, that puts you in a position to build hypotheses and quantitatively test them, either by comparing data sets or by using models that integrate. Next. This is one of the newer observations that we have. This is it's a surface mixing ratio that comes out of a column measurement for carbon dioxide. It comes from our orbiting carbon observatory satellite that was launched about 1.5 years ago. And you can see the color scheme. It's a fairly small variation, between 390 and 405 parts per million. Over the course of the year, you could see it move. The data set really was just released publicly like a month or two ago. And over the course of the year, you get a variation where you're showing the data because the technique works better in the hemisphere that has more sunlight. So in the winter, you see more data in the southern hemisphere, and then as you get into the winter, further into the winter and into the spring, you can see more data in the northern hemisphere, and you can see the spatial variations. You can see the seasonal variations, and at this point it's still a new data set, but people have worked on it very hard. It looks very good. They're building on sort of knowledge and practice that they got looking at similar observations from the Japanese GOSAT satellite that was launched in 2009. So there's a lot of cooperation and mutual learning when we try to advance to do these kinds of things, because this is a tough measurement, because you're looking at any one time at fairly small variations, so that means that you need to have enormous stability and precision so that you make sure that when you see a variation, that it's really a variation in CO2 and it's not just, well, you know, measurements, it's mostly right, but it can vary a little randomly. For something where there's this little variation, you're looking at carefully, you've got to beat that precision down really well, and that's what they do with this. Next, something else a little bit about precipitation. Working with our partners in Japan, we launched the Global Precipitation Measurement Mission with a dual frequency radar that Japan provided. The idea then is that helps connect the satellite observations from a variety of passive microwave instruments. It will be a mix of research and operational satellites. And what you do is you try to get to 3-hourly precipitation data. And precipitation is something that you really need to get with a fairly high sampling frequency, because you know from experience that there's a strong diurnal variation in precipitation. Like if you live in areas with large convective precipitation, you don't typically get a lot in the morning, but you'll get a lot in the late afternoon and early evening. Some other places, you go out in the Great Plains of the United States, you get a lot of nighttime precipitation. But you build it up where the GPS satellite really helps connect things, but you get this 3-hour product by integrating from a variety of different satellites, and it's a great example of how by pulling together different observations from different sources, you can build up a data product that's really useful. Because if you think about it, this kind of global precipitation information, it's an enormous benefit. There's so much of the world where you don't really know what the precipitation is. This builds on the success of TRMM, the Tropical Rainfall Measuring Mission that we launched with Japan. We launched that in 1997, well actually they launched it in 1997 on a 3-year mission, and that mission finally ended after 17 and a half years with the satellite returning to Earth this past year. So it's a great collaboration, but now with GPM, it's a higher inclination orbit, so we can get to higher latitudes. It's a dual frequency radar, can look at weaker precipitation and also look at snow. This represents a significant advance that I think we're really excited about that, and are looking to, say, help work with our partners to try to get that assimilated into weather forecasts. Next. This shows 3 years of sea surface salinity. It was measured with the Aquarius satellite. It's a partnership that we have with CNAI, the Argentine Space Agency, and it just satellite recently. The satellite bus stopped working after 4 years, so this represents the first 3 years of data. This is another one of these things where the variation is relatively small. It's plus or minus about 15% in what's called practical salinity units. So the salinity of the ocean, it's really important because salinity helps determine density. Density helps determine where water rises and where water sinks, and that helps determine the three-dimensional structure of the dynamics of the ocean. So this is the first satellite that was built really exclusively for studying ocean salinity. European Space Agency had done a satellite a couple of years earlier, soil moisture ocean, SMOS for soil moisture ocean salinity, that was sort of had to try to optimize to get both. This one was focused specifically on sea surface salinity, and you can see some really interesting patterns in how they change. lower salinity in the central tropical Atlantic, where you've got more precipitation, higher salinity in the sort of mid-latitude oceans where you have less precipitation. Atlantic tends to be saltier than the Pacific. Some areas where you've got a lot of evaporation and very little precipitation,